This time I want to discuss the effects of the offset voltage of op-amps. The offset voltage appears in the expression for the output voltage of an op-amp here. In an ideal op-amp, the output voltage is just the open loop gain A times the difference between the voltages on its two inputs. But for a real op-amp, you have this third term here, the offset voltage. And as you can see in the table of typical values of the op-amps that we've been considering so far, offset voltage tends to be around a few millivolts. The effect that it has on an op-amp circuit depends on the gain. The offset voltage is likely to produce an offset in the output of the op-amp of around about the offset voltage times the gain of that amplifier. One way to think about the effect of the offset voltage is in terms of an equivalent model of an op-amp, this one here. Here we have an ideal op-amp with an additional voltage source on the non-inverting input. And it's that voltage source which has a value of the offset voltage. This entire circuit here in the rectangular block is then a model of a real op-amp, with its non-inverting, inverting input and output. If you think about it in this way, then the effect of the voltage offset on the output of the op-amp can be easily determined by using superposition. It's just another voltage source. And if we consider only the effect of this voltage source, then in the case of a non-inverting amplifier, we'd have a circuit like this. And if we include the effect of the offset voltage in our circuit, we'd have an additional voltage there. So the total voltage on the non-inverting input of this ideal op-amp is Vin plus V offset, which means that our output, V output, is just the gain, 1 plus RF over R2 in this case, times the voltage on the non-inverting input of the ideal op-amp part of our model, which is Vin plus V offset. Or, write that another way, V out is the gain times the input as we're expecting, plus the gain times the offset voltage. And that is a term which is creating a DC shift or offset in our output voltage. Now that can be a serious problem if you have too much gain in a single stage of your op-amp. And we commonly do have very large gains if we're trying to amplify up the small output of a sensor, for example. It's quite possible that we will want to have a gain of around about 1,000 or so. And in that case, if we have an op-amp with a gain of 1,000 and an offset of 5 millivolts, that would predict an error in the output could be up to 5 volts. And if we've got an op-amp which is only powered from a 0 to 5 volt power supply, that could easily send the op-amp into saturation, just due to its offset voltage. When we're trying to amplify up very small signals at very low frequencies, DC, then there are some specialist op-amps with extremely low offset voltages that we can use for those applications. If, on the other hand, we're concerned with AC signals, then there are some other circuit techniques that we can use. For example, consider this circuit. If C, this capacitor here that I've called C large, is big enough, then at all frequencies of interest, it's going to look like a short circuit. Remember, the impedance of a capacitor is 1 over j omega C, so if C is big enough, the capacitor will look like a 0 ohm resistor. And in that case, the gain of this circuit is 1 plus 999 over 1, in other words, 1,000. But at DC, where the offset voltage gives you a problem, the impedance of a capacitor is infinite, which means that for this circuit here, effectively this is what it looks like at DC. But that's just a voltage follower. V out is equal to V in. So we have a circuit here with a gain of 1000 at all of the frequencies that we're interested in, but a gain of 1 at DC. So it doesn't amplify up the offset voltage, but it does amplify up our signal. But again, you can only use this technique if you're trying to amplify signals which do not extend all the way down to DC. Final thing I should mention about offset voltage is that many single op-amp packages have 2 pins for offset nulling, and you wire them up like this with a potentiometer here, and you can adjust the offset voltage of these op-amps to try and get rid of the offset voltage. It's an expensive thing to do in production because you have to individually adjust every single op-amp that you put into any piece of equipment because they will all have slightly different offset voltages. The actual offset voltage of an op-amp cannot be known in advance. It depends on the tolerances of the manufacturing processes in the op-amps themselves. And whereas the data sheets will give you a typical value and a maximum value of the offset voltage, they can't tell you what the offset voltage is going to be. If they could do that, they could arrange to cancel it out in production. That's all I need to say about offset voltages. Next time, we'll have a look at the effect of the finite output impedance.